Hello, everyone. Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gill Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries and constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gill@eapen.info. My guest today is Professor Claudia de Rham, who's Professor of Theoretical Physics at Imperial College London and a member of the American Academy of Arts and Sciences. She researches gravity, particle physics, and cosmology in pursuit of a more fundamental description of the nature of our universe and the laws that govern it. Welcome, Claudia.
Hi, how are you?
Yeah, thanks for doing this. So you have a book out. It's called The Beauty of Falling: A Life in Pursuit of Gravity. I love this book. I don't know about the title though, Claudia. I have vertigo. I have severe vertigo. So
Oh
I don't think
no.
there is any beauty in falling. But they tell me that if you fall in space and you scream, nobody will ever hear you. So that's sort of comforting. Um, and so what's the book about?
Uh, as as you can imagine, it is about gravity in many different ways. So the beauty of falling, in some sense, is the beauty of gravity itself and some of its universal nature. It's also the beauty of falling in the sense almost of failing, or in many different ways. In the fall, in the sense of letting yourself go, the beauty of embracing what is to come, and some sense the beauty of the space-time, just taking that and embracing it. But also, a lot of us may think of falling in some sort as failing, maybe, and it shouldn't be, but there is in gravity an element of the theory we have to describe gravity at the moment, the best theory, possibly the best theory that ever existed, which is Einstein's theory of general relativity. I think one of the reasons it is so perfect is because it predicts its own failure. So it predicts its own falls, if you were, its own
Yeah.
pitfalls. And that in itself is it's really extremely profound because it allows you to know when there is something else to uncover. It really provides you some sort of a window for opportunities for the future. So the beauty of falling is also in understanding that when you fall, there's something else to embrace coming afterwards.
Mm.
And that's where I'm coming from. So many failures in my life. I've fallen down many times. And it's not enjoyable. The fall itself is definitely not enjoyable, but it is an opportunity. And so it's embracing this opportunity for the future.
Yeah, that makes sense. So I want to get to the sort of the details of this, Claudia. As I mentioned, I don't know much about astrophysics, and I came from a sort of engineering and economics background. Um, and so they have been so there's an issue here. So we have so four fundamental forces, as they tell me: gravity, electromagnetism, strong and weak forces inside an atom. The last two we can probably not talk a lot about it. So gravity and electromagnetism. And electromagnetism I understand is mediated by photons, light,
That's right.
and gravity. We don't quite know, right? So the way that I think about this, Claudia, you correct me if I'm wrong about this. So I think about general relativity as sort of some sort of an elastic medium where you put a mass on, the space-time sort of warps, and I can sort of intuitively understand how
Yep.
that create gravity. So do we really need a particle to mediate?
That's a really good question. So one thing that whether or not we want to think of the particle, there is very much this element, and I think it's some sort of broadcasted to some level, that gravity is unlike the other forces of nature, that it's not a force, it's more the realization, the materialization almost of the curvature of space-time in which you find yourself. That's how you feel this notion of gravity, but it's really the curvature of space and time unified around yourself. And that is definitely true. It's an outstanding way to understand gravity and the way it acts on us and the way we act on it, and this sort of dance we have with gravity. But we also know that it's much more profound than that, and we know it's not even theoretical. We have observed gravitational waves. Those are great waves of gravity. We call them gravitational waves. On Earth, there's some another notion of gravity waves. That's not what I'm talking about. I'm really talking about gravitational waves, which are sort of this life of the curvature of space and time themselves. And they are very much the analog to light. So if you think of the electromagnetic force, this is mediated by, at the particle level, by a photon, but you can have more electromagnetic waves. You can think of it as a lot of them, a lot of these quantum of photon will make up electromagnetic wave at the classical level. And that's just a fancy way to say it's light. We do see light, and we do see this wave of the electromagnetic field. And the same is true for gravity. We have observed, we have felt those waves of the gravitational field. We have felt these waves of gravitational waves. And so there's a direct analogy there on how we understand and see light and understand it at how the propagation of the electromagnetic force is done at a more fundamental level by a fundamental particle, the photon. And so this analogy goes through all the way up to gravity and how we can think of it as the propagation of something more fundamental. I think maybe one of the questions underlying what you're asking is about the quantum nature of gravity itself. We have observed gravitational waves, that is a fact, but doesn't mean necessarily that there is such a thing as a graviton. Is gravity necessarily a quantized phenomenon, just like the other fundamental phenomenon of nature? And that's a very fair question. One of the things about gravity is that it connects everything. It has some sort of equivalence principle. So it connects with electrons, it connects with the light, it connects with itself, it connects with any system that exists. You put anything in space and time, like a mass if you want, and that will have an effect on gravity and create some curvature, and then through this curvature, that mass will then propagate in a different way in that space-time because it feels the curvature, it feels its own curvature. So there's some sense of back reaction. An object, a mass, can have an effect on itself through back reaction of the space-time in which it lives in. And anything lives on the space-time. So any object, not only just a classical mass like a star, but even a more fundamental particle like the photon or the electron, which we know very, very well that they are quantum in nature, those have an effect on the structure of space-time through gravity, and the structure of space-time will back react on them. So if you have a quantum system, you should satisfy the quantum laws of probabilities. There are specific laws of probabilities, and those have to interact with other quantum systems. But we know that gravity connects with them, they interact with them. And so for the laws of quantum nature to make sense, in some sense to preserve the laws of probabilities, if you want the adding up probabilities for a phenomenon to happen, it should add up to 1 and not to something imaginary, not something complex or even negative or larger than 1. So for the laws of probabilities to make sense and to satisfy something which we call unitarity, so probabilities add up to 1, anything with which a quantum system interacts should also fundamentally be quantum in nature. And therefore, fundamentally, gravity has to be quantum in nature. There's no choice about it. Otherwise, all our laws of quantum mechanics or quantum field theory would just fall apart. So there should be a quantum nature of gravity, but that doesn't mean we have observed it.
Yeah. So this is sort of the fundamental question, right? So without knowing anything about physics, I sort of like symmetry. I like things to be sort of explainable in a symmetric way, and I don't like a force out there that is, sort of very different from anything else. And one of our observations and data tells us that we haven't quite understood it, and so perhaps sort of natural direction would be to say it would be one of the things that we have actually mathematically categorized like formula or something like that. Is that the way that you're thinking?
Yeah, absolutely. The symmetry, the very notion of symmetry is really fundamental in the way we think about everything at the more fundamental level. So the photon itself, the way we think about it is very based on symmetry, some sort of local symmetry. And there is a symmetry embedded in how we represent electromagnetism in itself. Now, gravity, independently of the other forces of nature, gravity, as described by Einstein's theory of general relativity, was very much set up under some of what we call Einstein pillars, which are very much based on symmetry. The equivalence principle itself shows that there's some level of symmetry being there, but more fundamentally, understanding that any observer should see the same thing, should experience the same thing, should describe the laws of nature in the same way, independently of who you are, where you are, who you are, how fast you move, if you're around a black hole, if you're if you're on Earth, or if you're in the middle of nowhere, that completely flat space-time. The way you describe the laws of nature should be the same. You shouldn't be observer dependent, and it shouldn't matter on too much on your perspective. And so that calls for some notion of symmetry itself, which we call, the fancy way to call it is coordinate invariance or diffeomorphism invariance, nonlinear diffeomorphism invariance, but it's really telling you that you can be an observer and you can decide to describe the space-time with a particular notion of space and a particular notion of time, or you can be another observer and you have your own way of wanting to describe what is going on around you, and yet you should be equivalent. So that is, in some sense, a notion of symmetry. So this notion of symmetry is really rooted in the description of gravity in Einstein's theory of general relativity.
Yeah, I mean, there is clearly something inelegant about our inability to combine four different things. And we've been trying for a long time. And you call it glide. And I quite like that.
So yeah, I think you're absolutely right that the notion of symmetry and how to promote the symmetries we are allowing ourselves to think about is playing a crucial role on how we want to try to unify different phenomena together. So that was the case for the electric and magnetic force built into one framework, which is electromagnetism. The same was true once you brought in the weak force. It was embedded in something with its own symmetric group. And as you go on and include a strong force as well, you expect to go to a larger symmetric group, which even higher level of symmetry. And then in the past century, for many years, people have thought about the idea of supersymmetry, which is an even higher symmetry group in a way to try to incorporate gravity with the other forces in a sense of supergravity. And it has made incredible progress. And actually string theory, which is one of the most remarkable possibilities for a theory of quantum gravity at the fundamental level, it is really based on a notion of supersymmetry. We needed to have an extended symmetry group to be able to describe strings in a way which would include gravity, include the other forces of nature, and much, much more. We'll get much more than that in the process.
Yeah, so reading through your book, Claudia, I was thinking that status quo is the most powerful force that anybody has ever experienced. You talk about this in the academic context, the same thing happens in business. To change something, to change an established notion, is very problematic in many ways. So this is, but you know, we are in a situation that we don't quite have explanations for this integration, even though we've been sort of trying it for 100 years, right? So we have to try new ideas and new things and new experiments and new ways to think about it, right?
Sorry, I'm really sorry, but I'm having real trouble hearing you, and there's a big background noise. I don't know what it is. I'm really sorry.
Can you hear me now?
I can hear you, but there's
Still
okay,
bad.
that's much better now. Yeah. Yeah, banana's much better.
Can you hear me now?
You are quite soft, and there's a buzzing noise on top of you. Yeah, this is very loud now. Yeah, okay, now that's better. But I can't hear you.
You cannot hear me anymore, right?
No.
So let me. Can you hear me now?
Very softly.
Can you hear me now?
Yeah, that's great. Yeah.
Okay, so let me try a different route here. Is this okay?
Yeah, this is good. Yeah, yeah.
Okay.
However, I couldn't quite hear what you were saying
Yeah,
just before.
so just 1 minute. So what I was asking was, Claudia, that so we haven't been able to get these 4 fundamental forces together for a long time. We've been trying, and a lot of different ideas came through. In a situation where we haven't quite gotten to where we want to, new ideas have a lot more value than status quo. So status quo is, seems like, I have invested 30 years into this theory, and if anybody challenges me, I'm ready to come down with bricks and mortar.
Yeah.
Seems like the idea right here.
I mean, status quo for 30 years is not a big status quo. Well, some things take thousands of years to get developed. I'm not suggesting it should take that long, but the theory I have been working with, which is not there to unify gravity with the other forces of nature, but was on a status quo for many, many decades, something like 8 decades. So, I mean, it does happen. I think in the case of unifying gravity with the other forces of nature, it is a little tricky in how to even formulate think about it. So we know, as I was saying, we know that as described by Einstein's theory of general relativity, the theory breaks down at some point. We know that because the theory would predict otherwise some observables, some quantities which could in principle be measured if you're crazy enough to try, that would be as large as you want, even potentially infinite, and larger than the Planck scale, which is the scale of which you wouldn't even trust the classical result anymore, and quantum corrections would be in. And we know that happens, for instance, when you go very close to the center of black holes. As you go through the horizon of a black hole, that's all absolutely fine. You would die, and okay, but you would have your laws of physics, and you would have your theory, Einstein theory of general relativity, which will still be completely valid as you cross the horizon of a black hole. You can go inside the black hole, go closer and closer to the center of the black hole. And it's only really when you get extremely close to the center of the black hole, then we know that the theory of Einstein theory of general relativity breaks down, because it gives us some curvature invariants which are way too big to make sense.
Yeah.
And the same thing happens if you go very close to the Big Bang singularity at the very beginning, very beginning of the universe, very early on. But in saying that, I'm talking about a point in space, and I'm talking about a time in the history of our universe, and I'm using words that I'm used to talking about space and time, because that's the way I think about it. We can't think so abstractly in a way that we don't even have space and we don't have a time. But when we say that GR, general relativity, breaks down, the very notion of space and time themselves have broken down. So I shouldn't even use those notion of space and those notion of time to try to ask myself the question of what happens. I'm trying to ask myself what happens as I get very close to the center of a black hole, but probably the notion of what I mean by that and where I am and what space and times are not the right way to think about it. And so I don't even know how to formulate the question. And by that, I don't mean me personally, but it's very hard to even appreciate how we should formulate more concretely the question. And so it's not surprising we don't have an answer. Most of the time in physics, being able to understand what is the right question to ask ourselves is 90% of the work. And then we can actually go about and answer that question. But we don't even know precisely how to formulate those questions. It's very tricky.
Yeah, so without knowing anything about this, Claudia, I think of a black hole as sort of a hole on space-time. And so anything that is inside there is no space or time in there, in some sense.
No, but there is. Yeah, there is. They get reverted a little bit so that space and time flow, maybe not in the same way as you would have expected from the outside of a black hole, but as you go through the horizon of a black hole, through the surface of a black hole, the very notion of space and time make complete sense still. They do make sense.
Okay.
You may not like what happens to you physically, because 2 points can get stretched apart and pulled apart and compressed. So it may not be a particularly pleasant experience, but someone can describe what is happening. The very notion of space and time and Einstein theory of general relativity does make complete sense as you go through it. So space and time don't disappear as you go through the black hole. They flow in slightly different, counterintuitive way, but that's okay. We can still describe them. We can still ask ourselves the same type of questions as we used to. We wouldn't, because we wouldn't survive that, but that's a different question.
Okay, so you're saying that only at the discontinuity, only at the end of it.
Only at the center, at the very center. Yeah.
Okay.
That's right.
So going back to your book, so we have this complication of gravity. We don't quite know how to integrate that into the some sort of universal framework. And your hypothesis is that gravitons, that there's some mediating effect here, and the gravitons have some mass. We don't know what it is. We had some astrophysicists here talking about neutrinos. Initially, we thought there's no mass to it, but now we think there's some very small mass to it. So your hypothesis that gravitons have potentially some very, very small mass to it, right?
That's right. So let me maybe say a few things about that and where that comes about and what I mean by this and what other people think about. So in terms of gravity being mediated fundamentally by graviton, this is not me thinking that. This is quite standard way of thinking in general relativity in the community. So if you think of gravity and you try to think of it more as the same footing as the other very successful fundamental phenomenon in nature, then it's very natural to think of gravity as being mediated by a graviton at the particle level. So, and that is not, I think most people would agree on that. It doesn't mean we have detected a graviton. We probably would never detect a graviton. We can detect photons, for instance, but gravitons would be quite challenging. But we have detected gravitational waves, and we have very, very strong reasons to believe that fundamentally they should be mediated by a quantum field theory and a quantum of these excitations. So that would be corresponding to a graviton. Now, the reason we are thinking of the graviton being not necessarily a massless particle, as it is in Einstein's theory of general relativity, and rather one that has a mass, as in a massive particle, is not so much to unify gravity with other forces of nature. That wouldn't help very much at all. I mean, sometimes it may help you in terms of thinking about what is possible and thinking about how some of this aspect gets quantized. It can help you in the thought process, but it's not the original intention. Yeah. Rather, the original motivation is more in some of the observations that we have for gravity, something which is not predicted theoretically, like the fact that GR breaks down at the center of black holes, but something that has actually happened to be observed, which is that our universe is expanding, meaning that the very structure of space is stretching. If you look all around yourself, you see that faraway galaxies are receding from us and moving away from us at a speed which is faster the further away we look at. Yeah. And actually this expansion is accelerating, so it's going faster and faster. And that is quite counterintuitive, because you would have thought that even though if the universe started being from a big bang with a huge expansion, you would probably have expected that at the end of the day, all the masses, for instance, all the galaxies, all the presence, all the pool being present in the universe will ultimately slow this expansion down. Just gravity win, it's an attractive phenomenon, so it shouldn't make the universe keep on expanding faster and faster, but the other way. And what we have observed, not me, what cosmologists have observed is the fact that the expansion of the universe is accelerating. And that has been confirmed with many different probes, on many different scales now, with various stages of the universe. So we have very strong indication that the expansion of the universe is accelerating, and that is somehow counterintuitive. Yeah. Now we could, in principle, explain this with the fact that everywhere living in the universe, everywhere, absolutely everywhere, around here on Earth, but also in space, and particularly in cosmic voids in between the holes, the voids between clusters of galaxies. The fundamental fields that we are made out of, the Higgs, the electron, everything, they are still living at the purest possible state. In the nothingness, their soul still exists, if you were. There's some vacuum of those fields everywhere in space and time. And this very possibility that any field can have a small excitation anywhere it wants, even a small quantum fluctuation, means that what we think of nothingness, what we think of a completely empty space, the complete void, is actually not empty per se. It carries the soul of all the quantum fields that are omnipresent in the whole space and time, in the whole universe. And those carries an energy density. And that energy density by itself actually would lead to the accelerated expansion of the universe. So it's a very good candidate, and so far, so good. Everything seems to make sense that because of the quantum Soul nature and the quantum vacuum energy of all the particles that we know, it leads to a vacuum energy that leads to an accelerated expansion of the universe. But this accelerated expansion would be way too fast, way too fast. So fast that if you had something which was just 1 centimeter away from you, it would be receding away from you at a speed faster than light. So you wouldn't be able to see, your observable universe would be just be very, very small. And clearly that's not consistent with observations for you.
So let me see if I can understand this, Claudia. So there's a vacuum energy.
Yeah.
We can measure it, right?
No, the vacuum energy by itself, we can't measure it. The only thing, no, it as soon as with our instrument, with us being made out of material, if you want, we don't necessarily, we don't measure the vacuum energy. We measure our interaction with, for instance, light, with the quantum fields, or an electron with those. So by definition, it's not the vacuum energy we would measure there. It's the interaction with it. To be able to feel this complete vacuum energy, what you need is its effect on the purest possible way on space-time, with nothing else touching it.
Right. Okay.
And so gravity is the one that feels it.
Okay, so I don't think I understood. So our expectation of the universe's expansion is higher than what we really observe.
That's right. Accelerated expansion is much higher, much higher.
So expectations are a lot higher than what we actually measure.
Yes.
And there has to be a reason for it.
That's right. That's right.
And so your hypothesis is that gravity is not infinite in the sense that it doesn't have an infinite range in some ways.
Exactly.
I don't know much about this, Claudia. I'm just making this things up. So hence, when things sort of go out into high scales, things would slow down because of this gravitational, as you call it, relaxation, so to speak. Right?
Exactly.
So that's the hypothesis. Yeah.
That's right. So this, in Einstein's theory of general relativity, the fact that the graviton is mediated by a massless particle, it's you may think of it as something which is universal, something which is beautiful, but it also occurs in some sense that it never stops. It never stop caring. So it cares, and it carries all this vacuum energy accounted for in the whole universe, which is huge, is absolutely huge, and that should lead to a huge accelerated expansion of the universe. But perhaps this is the only question I'm asking, the only question my collaborators and I are asking is it too much to ask that gravity should care about this infinite amount of vacuum energy, if you were, and everything with the same carrying with the same level on all possible distance scales? Maybe that's too much to ask. Maybe comes a point where enough is enough. It's being very good to take into account all of those contributions for all those distances, for all that huge amount of time in the history of the universe. But maybe it's time for it just to relax a little bit and say, okay, that's enough. Now I don't care anymore. Really, I got enough. I wouldn't blame it. So this seems a bit strange. It probably seems strange as I'm talking about force, but I'm talking about it having a finite range. That's what I'm talking about. That after a while it just relaxes out and stop caring about everything that it should otherwise be carrying. But this is a very familiar concept in the other forces of nature.
Yeah.
So you mentioned them, the other forces of nature. For instance, you mentioned the electromagnetism, and you mentioned the weak force, and then you say, well, we're not going to talk too much about it. And the reason is because we're not so familiar with it. We're not as familiar with it than electromagnetism. we do see light. We're very, very sensitive to light, but as human beings, not very aware of the weak force, and we're not very aware of the weak force because it's weak. And the reason it's weak is because the particles that carry it are massive. They have a mass. That's the W and the Z boson, and we do know how they can acquire a mass from the Higgs mechanism. So this is all extremely well understood. This is not me making it up. This is all very well understood science and physics on how you have a Higgs that creates some vacuum energy leading to some inertia for those massive particles, the W and the Z boson, so that when they propagate, the inertia is actually quite large and they don't want to go very far. They want to stop quite quickly. So that is that relaxation mechanism I'm talking about, that it doesn't want to propagate for an infinite range and carry a force which has an infinite range along the way. They just want to stop very quickly because it's painful to drag along this big mass and this friction with the Higgs field surrounding them.
Yeah, so as you said, the W and Z boson, it's so they cannot go too far because of the constraints surrounding them. Because of the mass, because of the Higgs.
Because of their mass, yeah, that's right. Their mass is acquired from the interaction with the Higgs, Higgs field, the underlying Higgs field, yeah.
And so the Higgs did not exist for whatever reason. We would not have this universe, right? I mean, everything would be flying all around the place.
That's right. The weak force would not be weak. That's right. So it'd be very different. The very structure of atoms would be very different. You and me would not be having this discussion.
Right. So going back to, again, gravity. So I know that you have done some work in this area too. This idea of multiple dimensions of space.
Yes.
They have been, sort of string theorists. A lot of string theorists came on the show as well. Claudia. I know nothing about it, but we are still struggling. It seems to me we are still really struggling to have a unified theory of these forces, right? So where are we in the current situation?
Yeah, so the extra dimension came about exactly from string theory or superstring theory, in that, funnily enough, for that theory to make sense, and so the idea of string theory is really beautiful in expressing particles actually as excitations of strings in various ways and having quite a beautiful symmetric group. You cannot describe strings which excitations actually match up precisely that of the graviton and any other higher spin particle. So you could include the fundamental forces of nature, the electromagnetic force, the electroweak force, and gravity, and potentially other forces we haven't even yet observed in nature. But for them to be consistent, funnily enough, you need to cancel some some sort of unwanted contributions, and those cancellations only occur if you have quite a large number of dimensions. And it is funny for me to even appreciate that those number of dimensions is an integer. When you go through it, it is not even clear to me that it had to be the case that it was for an integer, a positive integer number of extra dimensions, that it could happen. To me, this is really incredible, because it could have been that it's only for negative number of extra dimension or something like that. But no, it is actually for something which is, I'm saying that because if you think about extra dimension, it may seem a bit crazy, but actually it's not so crazy. It's a finite integer number of extra dimensions. So that's not crazy in some sense. You could have some other dimensions of space out there, and we wouldn't necessarily observe them, because all the fundamental forces apart from gravity that we would know of, they could be, well, for multiple reasons, they could be extra dimensions. One of the reasons is that they could be very, very small. So when we look at them, we observe with physics, for instance, at the LHC now, at CERN, we observe very small distances, but at distances even smaller than that, it's possible that the extra dimension we would be able to see them. But so far, we're not seeing such small distances. So very, very subatomic distances, very, very subatomic. Maybe those extra dimensions have the scale of the Planck scale, which is 10 to the minus 32, 33 centimeters. So extremely, extremely small. And you would need to run experiments at the Planck scale, so 10 to the plus 19 giga electron volt, so 10 to the 27 electron volt. So that's 10 to the, let's see if I can do that, 10 to the 15 times the order of magnitude as what is at the LHC at the moment. So really, really high energy to see them. So that's the most likely reason why we don't see, even if according to string theory, there would be extra dimension, we may not see them because they're so small. But another possibility complementary to it, so you can have both complementary to each other, is that some of those dimensions may not be so small, but we don't observe them because light, for instance, and all what we are made out of, all the matter we're made out of, all the standard model particles, they're confined on our brain, on our surface, within those extra dimensions. So it's a little bit as if you're looking at a pond, you're looking at the surface of a pond, and you have these water spiders, this surface water spider that just live on the surface of the pond. And they may experience some phenomenon, but for them, all that exists is the surface of the pond. They're not ever able to go within the depth of the water like the fishes. But things happen in the depth of the water that have consequences on the surface of the water. So if a fish wiggles and woggles and there's some air bubbles within the depth of the water, it will have an effect on the surface for these little animals, but they would experience that in a very funny way for them because they don't appreciate this depth of the water. And so it's possible that this is what, in some sense, is happening to us. We are just experimenting on the surface of a brain, and then gravity itself is able to probe this extra dimension, the depth of this extra dimension. And so that's why gravity itself may look a little bit different from the other forces. And understanding that could have some big impact in how we understand the evolution of our universe, for instance.
Yeah, so we had some different ideas around this, right? So we had M theory.
That's right.
Which was sort of thinking about a observable large dimension outside the 4 dimensions that we have.
That's right.
What's the status of that nowadays?
Well, it's when I started my PhD, we were hoping, not me personally, but the community almost was hoping that we could have one of those extra dimension motivated by M theory. So M theory is so self-taught. Let me backtrack a little bit. There's multiple different realization of string theory, and one can understand they are dual to one another. They are the same theory in a different way, and they're symmetric to each other. And it seemed almost as if you can see different parts of a more fundamental underlying framework. And so this underlying big framework was called M theory. Witten came up with that. I don't know what it's M for. It could be mother, it can be magic, and
not even Witten knows what it stands
for.
No,
and I think that's part of the mystic part of it. So it's this unknown big thing, but for it to make sense, it would require at least one extra dimension. So instead of being in 10 dimension, like in string theory, it would be 11 dimensional M theory, where the 11th dimension could be slightly bigger or quite larger, or potentially observable than the other ones. All of those ideas came up at the very beginning of the year 2000, the end of the past century, and the beginning of this one. That was before the LHC was switched on, before we could observe very small distances, and at the time there were loads of possibilities being discussed that this extra dimension was actually quite large, maybe as large as a millimeter in scale, or a bit smaller, but quite large actually from the macroscopic point of view, from the particle physics, point of view. And so gravity could leak within that millimeter scale extra dimension, while the other forces of nature would be confined on a brain in that extra dimension. By now, we have observed phenomena at a much higher energy with the LHC, and so it couldn't be quite 1 millimeter. It should be even smaller than that if we have an extra dimension, or it has to be, I mean, it can't be so simple as that, but we can still have one large extra dimension. It can't be millimeter scales large, but a little bit smaller would still be okay.
Yeah, you guys killed joy, I just hoping that all this, all these things that are sort of parallel, 1 millimeter apart.
Yeah.
There's so many different universes out there and all of that stuff. And you guys say, no, that's not quite true.
Well, it could still be. It could still be. Maybe not 1 millimeter, but yeah, you need to make them a bit smaller. Could be. I don't know.
And so we are back to sort of square one in the sense that gravity is still not playing properly. There are a lot of ideas, of ideas around it. I love your idea, actually.
Thank you.
Personally, I mean, I know nothing about it, but it seems like in the right direction to say that. I mean, quantum mechanics drives. Our latest understanding is that quantum mechanics drives everything. So there cannot be one force that's sort of not playing with quantum mechanics.
That is absolutely right. Yeah, that's right. That's right.
So
yeah, I mean,
go ahead. Yeah.
The way very much we think about it is very similar to the other forces of nature. So we don't start with the assumption that gravity is all about geometry. We much more start with gravity is the representation of a fundamental particle, like the photon is for the electromagnetic force. And so from the basic, we really put the particle in the quantum field theory at the basis of everything. With a description of gravity, which is very, very similar to all the other forces of nature.
I do like the sort of the geometric description of gravity, though. It's so elegant.
It is beautiful, and it's once you understand it, it's actually very intuitive. It has been such a leap forward in understanding of nature, understanding of physics. It is really beautiful. At the same time, I think there is something profound in gravity which we can express at the same level of particle physics as the other forces, and we need both. Just like there's a duality between the wave and the particle, and some phenomenon can be described classically and sometimes they can be described quantum mechanically. The same thing is true for gravity. There's a classical representation in some limit of gravity which is much more through the geometry, but it doesn't mean that it doesn't also enjoy a much more fundamental quantum field theory description of it.
Yeah, I mean, it seems to me, Claudia, I don't know much about this. It seems to me there's only one direction here, which is a quantum mechanical description of gravity is potentially the only way to unite everything, because something that's not playing with everything else that's playing in a system.
That's right. You need a quantum description of gravity, and we do have it. When I say we, as the community, we understand very well how to describe gravity at the quantum level at low energy scales. It's really when you go to very high energy scales that this quantum description of gravity, we know we are missing something. It requires more. Because by itself, otherwise, it doesn't make sense.
So we're missing something. So at the limit, in small and very large, we appear to be missing something.
That's right, exactly.
So does that mean that we don't really have the right idea? Maybe you miss the whole thing altogether.
That is possible, and I think for me that's part of the excitement. That's part of the opportunity. If we knew what he was, then we would be working on that, and maybe we'll give you the answer. But knowing that something is not quite working, it's something quite exciting, because it tells us there's really something to be learned from that.
Excellent. Yeah. Thanks so much for spending time with me, Claudia.
No, your pleasure. That's absolute pleasure. Yeah. Thank you for all the questions.
Thank you.
Thank you.